Hello, Calculus 3 students. I'm sitting on the floor, you can tell by the background material, because perhaps Her Royal Highness, the Cocoa Bananas, might walk by while we're doing calculus. So let's see. Doing two problems from the section that we were working on, center of mass and probability. So here we go. This is a find x bar, y bar, the region, and there she is. There's a weasel. Oh, look at her. Oh, look at that weasel. Hello, weasel. Are you going to do math with us? And she's not going to do math with us. So the region is this area between the two parabolas, y equals x squared and x equals y squared. And the density is square root of x. So that means that the further along you go in the x direction, the better the density is. And there's a weasel. Hello. So, well, to do the center of mass, we have to do the calculation of the total mass itself, which is the density added up over all the points in the region. So you integrate over the entire region. You can see the limits of integration. I have the top curve, square root of x, bottom curve, x squared, because I'm going with dy dx. You can tell by that little vertical box. So my limits of integration are describing the region, the domain, and then I have the density function. So this calculation isn't too bad. Notice that since it's dy first, I don't integrate square root of x. I just throw a y on there because square root of x is treated as a constant. And then I evaluate from square root of x to x squared. So I've got some fractional powers of x to deal with, so I've simplified them over there. Still didn't integrate with respect to x yet, but it's not too tough an integral. Integrate with respect to x, and a funny thing happens. When you go from 0 to 1, all that really matters is the coefficients, because the x's are all 1s. Then you write a minus sign, and the x's are all 0s. So this whole mess boils down to 1/2 minus 2/7, which, if we do it correctly, is 3/14. Now, if you notice, the very next integral that we do, x bar, has 14/3, because it's supposed to be 1 over 3/14. So I've just flipped that fraction out front, 14/3, which is fairly beefy. And I know my x bar has to be somewhere between 0 and 1. And it might be leaning a little bit toward the x coordinate if I do it correctly. I might get something that's just leaning a little bit more towards the x than the y. So let's see what we get. So I got the 14/3 from 0 to 1. This x squared to square root of x, same limits of integration as before. But this time the integrand, instead of just regular density function, there's a factor of x because we're doing x bar. The dy dx, I integrate and I just get the y. Then I substitute in those fractional powers of x. So I'm getting an x to the 3/2 times x to the 1/2, that's x to the 4/2. Then a minus sign, and x to the 3/2 times x to the second. Well, that's 3/2 plus 4/2, that's 7/2. And I still have to do the x integration there. So I get the one higher power dividing by the new power, and that gives me the same thing happens before. When the x is 1, you know, the fractions are, or sorry, the computation is just the fractions, the subtraction of the fractions, and there's a weasel. And when x is 0, the whole thing is 0. Gosh. And so I've got a 1/3 minus a 2/9. That's all I got to do. And then multiply by the 14/3 in front. So 1/3 is 3/9. 3/9 minus 2/9 is 1/9. So 14/3 times 1/9 gives me 14/27, just slightly greater than halfway. So I'm kind of surprised. I know with the density square root of x, it's more dense over here, but remember, this is the balancing point. So the balancing point is cheated a little bit in the direction of x equals 1, but not by much. Well, this is what we got. Now we're going to get y bar, and the y bar might not be cheated as much, or it might be cheated close to the center. Let's see what we get for the y bar. Same setup, 14/3, 0 to 1, x squared to square root of x, and then it's a y here instead of an x. Oh, now I'm doing dy dx. So this y becomes a y squared over 2. I pop in that fractional power of x and the x squared. So I've got a little bit more work there. And we're almost done. Just keeping track of these fractional powers, rewriting them, and then I still have to do dx. So each of those goes up by 1, and I divide by the new powers. So 3/2 becomes 5/2, but I really have 2/5 out front. 9/2 becomes 11/2, which puts 2/11 out front. And then when x is 1 and x is 0, all I really get is the 7/3 out front from the 14/6. That 14/6 came from 14/3 with an extra factor of 1/2 after that first integral. So I've got a 7/3 times this subtraction when the x's become 1s. So it's just 7/3 times 2/5 minus 2/11, which after some fraction work that you can see and study, I get 84 over 165, which is a pretty good answer. You know, it's a little bit bigger than a half, but not by much. I mean, just barely bigger than a half. So my centroid, my balancing point, if 1/2 is halfway up each of these things, my balancing point is just a little bit off of what would be like, say, the pupil of the eye if this was an eye. It's just a little bit closer to this corner than it is to the origin. And that's reflecting the density function. So I hope you like that. That was an easy one. That wasn't too bad. Let's do, well, I mean, look at it though. It's a pretty long calculation just to get the balancing point. Now we're going to do a probability density function idea that is an important idea. If you were going to study probability density functions, you'd want to know this idea. This was from Calc 2. It's a exponential density function where if you have mu, that's the lowercase m in the Greek alphabet, mu, and it stands for the mean, this probability density function actually has mean mu. So whatever that number is to the -1, it's e to the -t over that number. Otherwise, the function is 0. So when t is greater than or equal to 0, I have this exponential density function, which you can actually graph. It's as an exponential density function, it looks like this. It decays very quickly. But for any choice of mu, this area is 1. So you have the property of a density function. Well, one of the things you can do is you can build density functions from existing density functions. So the usual way is you might have two random variables that are independent, two things that you're going to study as a joint density function, but the two things that you're investigating are independent of each other. One doesn't affect the other. So there's the you could be doing a probability density function where one variable is the weight of a chicken over time, and then the other one is the photo period over time. Well, the weight of the chicken doesn't affect the photo period, but if you wanted to combine these random variables together into one joint density function, you'd be studying chicken weight and photo period at the same time. But since they're independent, we have a nice trick, and that is you can make a new density function from the old just by multiplying them. So I wanted to illustrate this idea to you. This guy, the way you can see it's a probability density function, it has the two properties. First of all, it's non-negative for every value of t. And the integral is 1. That was a Calc 2 integral. The integral of this thing is 1 when you go from -infinity to infinity, but you're really only integrating from 0 to infinity. So I just picked 5 and 6 for my two means out of thin air. So I got f of x, that's supposed to be an x, not a t. That's supposed to be an x. G of y, that's supposed to be a y. That's a y. So these are both probability density functions of a single variable, and we can make the joint density function out of their product. Dig it? It's a cool idea, because if these two things are not, if these two random variables, x and y are the random variables, f and g are the density functions. If x and y don't influence each other, then you can study them in conjunction. So you can see where this would be interesting in the investment industry or in the insurance industry, because you could be doing something where you have two things that you think are independent, some data suggests they're independent, but you can still do a joint density function where you can study probabilities of how these two things interact, how the probabilities work out, even though supposedly these two things don't influence each other. So I'm just going to demonstrate that this is still a joint density function. First of all, look at this product. No matter what t is, this is non-negative. So we've got that, and now we're going to do the integral and see that it's actually 1. So from 0 to infinity, 0 to infinity, and if you notice, wait, 0 to infinity, 0 to infinity, those are constants. This is an x, that's a y. These don't have anything to do with each other. We can do that really nice trick where we do the dx stuff, we do the dy stuff. The only thing we have to worry about is the extra minus sign, because remember, when you go to do the derivative by chain rule, the derivative of that power, or sorry, the integral by chain rule, when you go to do this integral, the derivative of the power is negative 1/5. So I need a negative 1/5, and I got to balance it out front. Oh, I also have to have a negative 1/6, and I balance that out front. So those two negatives are going to cancel. But I need these in place so I can employ the chain rule. And I employ the chain rule, and I get just this part. Because remember, I'm doing the antiderivative. So I get these two things. And these are really interesting to evaluate because e to the negative infinity we treat as 0. It's a limiting value. It's an improper integral. We know how that comes out. So in each of these cases, I have 0 minus 1, and they multiply and give me 1. So that's what's going on with the joint density function. I get the final answer is 1, and this is meant to stand for all the cases. So if you ever need to study a joint density function, that means you have two variables or more in here. One of the ways to make them is out of single random variable density functions, and just multiply. But remember, it's only when the random variables are independent. You have to have that. Well, you got to see the ferret. I don't know if you can hear her. She's still bumping around down here. But you got to see Miss Coco Bananas, and I will see you guys on Wednesday.